Le Chatelier's principle. So what Le Chatelier's principle says is that when a system is at equilibrium and it's placed under a stress, so it is changed in some way, we're going to look at those particular changes in a second, the system's going to undergo a shift in order to counteract that stress that's being placed on it. So for a system at equilibrium, generally speaking, when you take something away, the system's going to shift to try to partially replace what's been taken away. If something gets added to the system, it's going to shift in a way that will use up what's been added. So imagine we have reactants and products. We're going to be using the term shift to the right to refer to more products being formed, and we're going to use the terms shift to the left when we're making more reactants. So we're going to be talking about a shift to the left means the products are being consumed and making the reactants, and a shift to the right means the reactants are being used and making the products. And it'll be initially at equilibrium, it'll go through this shift, and it'll reestablish a new equilibrium with new concentrations of those reactants and products. So effective concentration. Essentially we have four options here. We can add a reactant, or we can add a product, or we can take away a reactant, or we can take away a product. So the effects are, if we add a reactant, it's going to shift to the right, and it will be using up that reactant that you've just added, because a shift to the right means that it's using the reactants and it's making more products. If you take away a reactant, it's going to be shifting to the left, and so it'll move to the left to try to replace, or not that it's doing it intentionally, but it will start replacing the reactant that has been taken away. Adding a product will shift it to the left, and taking away a product is going to shift it to the right. So whatever you do, if you're adding or taking away reactants or products, the system is going to shift in a way to counteract that change and then reestablish equilibrium again. Effective temperature. So if you think of energy as a reactant, if it's an endothermic reaction, so endothermics, the energy is going in, or if you think of it as a product for an exothermic reaction, it's coming out if it's an exothermic reaction. It works very similar to the reactant product being added or taken away. If you cool a system, the shift will happen so that more heat is produced. So if you have a system that's at equilibrium and you cool it down, it's going to shift in the direction that releases heat. And if you heat up a system, it'll shift to use up that extra heat. So if you have a system at equilibrium and you heat it up, it'll move in the way that will use that extra heat. And it depends on whether you're dealing with an endothermic or an exothermic reaction as to which direction that means. So effect on temperature. Again, we can add heat, and we have two options. We can add heat to an endothermic reaction, or we can add heat to an exothermic reaction. They have opposite effects. We can take away heat from an endothermic reaction or from an exothermic reaction, and again, they would have opposite effects. So if you add heat to an endothermic reaction, remember endothermic has the energy term on the left, so if we had our energy plus whatever the reactant is, and is in equilibrium with B, so we have an endothermic reaction. If we add heat to that system while it's at equilibrium, it's going to be shifting towards the right to produce more product, and in doing so, it'll use up some of that energy until equilibrium is reestablished. If we take away heat, so again, equilibrium reestablished, if we take away heat from an endothermic reaction, it's going to be shifting left in a way that, where's that button? All right, here we go. All right, so we take away heat from the system at equilibrium. It's going to be shifting to the left until it reestablishes equilibrium. And if we add heat to an exothermic reaction, we're going to see a shift to the left as well. Again, let's put this as an exothermic reaction. So as an exothermic reaction, if we were to add heat to this system here, it's going to be shifting to the left, so it'll move to produce more of those reactants. That's a way of using up that energy. If we take away heat from an exothermic reaction, it's going to be shifting right, because that will be replacing the energy that is taken away. Again, it's not that the system is doing this intentionally, but it is what happens, not why, but what. So here's a particular system if it's at equilibrium and it's an exothermic reaction. If we heat the system up, so we have this sitting in a jar at equilibrium, as written with the energy on the right hand side, if we were to heat up the system, it'll cause the system to shift left. It'll consume some of the products and start producing more of the reactants. So these values would go up. This value would go down in terms of their concentrations until it reestablishes new equilibrium at that new temperature. If we were to cool this system down, it's going to cause it to shift to the right. The reactants will be used up to make more product, and it'll reestablish a new equilibrium. Now, when we're changing the temperature, the K value is going to be changing. When we're changing the concentrations, the K value remains the same. So if we had this particular example here, another reaction, it's an endothermic reaction. Heating it is going to shift it to the right. Cooling it down is going to shift it to the left. Pressure on systems that have gases. So if the volume decreases, then the pressure increases. So you have this closed system sitting at equilibrium. If you decrease the volume, a corresponding increase in pressure will happen. There's going to be a shift to the side with fewer gas molecules. So if you bring the pressure up or the volume down, it is going to shift to the side that has fewer gas molecules. If the volume increases, so you bring your volume up or you bring your pressure down, it'll shift to the side that has more gas molecules. And if there's the same number of gas molecules on each side, then there's no effect on shifting the system. So for example, if we had this system here, we've got 3 different gases. On the reactant side, we've got 2 SO2s and 1 oxygen. And on the right-hand side, we only have 2 SO3s. And so there is a total of 3 particles on the reactant side and only 2 particles on the product side. So the reactant side has more particles. So if you shift it to the left, there's going to be more particle production. If you shift it to the right, you're actually decreasing the amount of particles in that system. So if you increase the pressure of the system, you're decreasing the volume, we're going to see a shift to the side that has fewer particles. In this particular reaction, that happens to be the right-hand side. If you decrease the pressure, then it will shift to the side, it'll shift left to the reactant side, the side that has more particles present. And again, we're not really explaining why this is happening, we're just stating what does happen. All right, try these out. So left or right? The temperature is raised in the system shown here. So we have ice plus energy, as you know, forms water. If that's sitting at equilibrium and you increase the temperature, we should see, as you would know, ice is going to melt. If you add energy to the system, it's going to be shifting right, because that is an endothermic reaction. And if it were at equilibrium and we added energy to it, it will shift right. All right, if NO2 is added to this reaction here, so we're increasing the concentration of the products, we're going to see a shift to the left. Now, we're not changing the temperature, so our K value is going to be the same, but we are increasing the reactants, so we're going to shift to the left. Water vapor is removed from this system here, so if we decrease the product, we're going to have a shift to the right in order to replace that product. All right, pressure increasing on this particular system. We've got 1 particle on the reactant side, 2 particles on the product side. So if we increase the pressure, it's going to have to shift to the left, to the side that has fewer gas molecules. Changes have no effect. So first thing is a catalyst. If you add a catalyst to a system at equilibrium, it can get to equilibrium faster, but it's not going to change where that equilibrium position is. It's not going to change the K value. It'll just get to equilibrium faster. So it will not affect the position of equilibrium. Adding an inert gas, again, if you're adding a gas to a gaseous system at equilibrium, you would assume that the pressure would go up. And inside the container, the pressure does go up, but if we think about the law of partial pressures, the pressure is due to, so that the total pressure in the container is due to the partial pressures of each of the gases within the container. So yes, adding an inert gas, so let's say we added in gas number 3 here, it would add pressure. It would increase the total pressure of the system. But according to, let's say, that reactant there and this product here, their pressure is exactly the same. Their individual gas pressures have not changed. The total pressure changed because the third particle, the inert gas, might have increased the total pressure of the system. But from the view of the reactants or the products, the pressure is the same for them. So their new pressure has not changed from their old pressure. So adding inert gas does not change the pressure of the reactants or the products, and therefore would not have an effect on equilibrium. Okay, concentration time graph. So if we were to look at this reaction, if we wanted to actually graph this over time. So let's say I have N2 and let's do H2. So those are our two reactants. And let's do our product. We got the Haber process here. So we're making some ammonia gas. So initially we'd assume the ammonium gas starts out low. Initially the reaction would be fast and would plateau. The hydrogen, it would start at something and it would get used up and it would plateau as well. And this graph is not to scale, so the numbers aren't actually going to work if you tried to plug the numbers in, but we're trying to get the idea of how the concentrations would change. Now, we know that the hydrogen is being used up 3 times as fast as the nitrogen. My slope is probably not exactly reflective of that, and the ammonia is being produced twice as fast as the nitrogen is being consumed. I'm not going to worry about getting the scale right for this graph. What I do want to focus on is, okay, if you have the system at equilibrium and you start doing things to it, what's going to happen? So let's say I increase, add some hydrogen gas to this system. So how you'd graph this, there's 2 things you have to worry about. The first thing is what the initial change does to your concentration. So if I add hydrogen gas, initially its concentration is going to go straight up. So it's going to go vertically upwards. The nitrogen didn't get added, so it doesn't change, and the ammonia didn't get added, so it doesn't change either. So I would just see this vertical line for the hydrogen gas because I added hydrogen gas to it. Then the question is, what is the effect on the equilibrium? So we know if we add a reactant, it's going to shift the system to the right. It's going to start producing more products from those reactants and reestablish equilibrium. Because we're changing concentrations here, the K value will remain the same, but we will see a shift to the right. And so we will see a initial jump in hydrogen, and then we will see it plateau down. As it shifts to the right, it's got to use up the nitrogen because that's the only way it is able to move right. So that will also curve down like so. It does not have the initial peak because we did not add nitrogen. And then the ammonia, because we're producing it, it will curve up like so and plateau again, and we will reestablish a new equilibrium. All right, let's look at the next one. So this is an exothermic reaction. So if I were to, let's say, heat up the system, so I increase the temperature. If I look at this system, I know my energy term it's exothermic, so I can imagine my energy terms over here. That says energy. And so if I increase the heat of this system, or increase the temperature of the system, that's going to drive a shift to the left. So what that would look like on my graph is if I start shifting left from this point, I'll be producing some nitrogen, and initially it'll be fast and then it'll slow down. I'll at the same time be producing 3 times as much hydrogen, and so it'll initially be fast and then eventually slow down again. Let's make sure nitrogen's got up there too. And then my ammonia, because I'm shifting left, it is going to be peaking down and then plateauing as well. So there's no peaks here. It is just going to be curving, and that is due to a temperature change. What you see the peaks with is when you have a concentration change, or let's try this one. If we have the pressure increase, so let's say at this point in time we decide to increase the pressure, and since we have 2 particles on the right-hand side and we have a total of 4 particles on the left-hand side, if the system's at equilibrium and we increase the pressure, the system is going to shift to the side that has fewer particles. And so in this case, it would be shifting to the right. The right has fewer particles. And so what we will see is if there's an increase in pressure, that's corresponding decrease in volume. And when you bring the volume down, so initially the volume is whatever it is, and you bring it down, the concentration should all spike upwards. And so, again, not to scale, I'm going to run into each other. It's okay if the lines cross, that doesn't mean anything. But if we increase the pressure by decreasing the volume, all of the concentrations are initially going to go up, and then we're going to see this shift happen based on the equation here. And so since the right side has fewer particles, it's going to shift to the right, and we're going to see that curve again for the ammonia, and then we will see the drop down, the consumption of the nitrogen and the consumption of the hydrogen at 3 times the amount, and we will end up with our equilibrium being reestablished again. And we can vary this. You can add other reactants or add other products, or take away reactants, take away products. You could cool the system down. Adding a catalyst would just involve continuing equilibrium along. It would not change the position of the concentrations, position of the equilibrium. And do remember that when we're, as long as we're not changing the temperature, your K value is still going to work out to be the same. All right, so let's look at this mathematically for a minute so we can better understand what it is that's happening. So when changing concentration or pressure, the K must remain constant. And so we're only changing K when we change temperature. So the K has to work out to be the same when we change the concentration and the pressure. So let's say we're changing the concentration, and so let's use this as our example reaction. Or we could set up our K expression for that particular reaction as B squared over A. If we decrease the concentration of B, so if we bring the concentration of B down, what we're going to see is that in our K expression, this value up here, the numerator, is going to get smaller. But remember, the K has to be the same, right? We're not changing temperature, so K has to be the same. So if we make the numerator smaller, that's going to temporarily change K. But we've got to reestablish equilibrium, and K's got to be back to what it was before. So in order to remedy this, A must be decreased. So if we bring down B, what that means is if we're trying to get it back to the same K value, we're going to have to lower the denominator because our numerator has been lowered as well. And so we're going to see a decrease in A, and essentially what that means is a shift to the right. We're using up that A, and in doing so, A will get smaller, and in the process, B will start to be produced more, and we'll re-establish the numerical value that K was originally, because again, K must revert back to what it was before the change happened, because K doesn't change well outside equilibrium, as long as you're changing concentration. Volume and pressure. So if we increase the pressure on the system here, so again, we've got 1 reactant and we've got 2 products. So if we increase the pressure, we should see a shift to the left. The numerator and denominator both are going to be increasing because we're decreasing the volume. So both of them are going to be getting larger, but B is squared. So however much B goes up by, A goes up by amount because we decrease the volume, so they both go up by the same amount. They both peak, as we saw in that graph there. However, the effect it has on K is squared for B compared to A. And remember, that is the number of particles of B. And so this is why we see a shift to the right, because in order to get back to our K value, whatever it was before we caused this stress, we're going to have to decrease B by more than we decrease A if we are to get back to our original K, because B is going to be squared. So the numerator increases more because of the exponent is 2 in this case. There's a greater number of gas particles. That's what it's related to, is the coefficient there. In order to remedy this, the concentration of B will have to decrease and A must increase. So that's our shift to the left, make more A, bring B down, make more A. That shift will happen until you reestablish the original K value.